everyone. It's great to be here. I'd like to thank the organizers for this wonderful workshop. My name is Kamal Choudhary. I'm a staff scientist at NIST. Today, we're going to discuss about Atom GPT for inverse material design. First of all, if you're not familiar with NIST, this is the oldest scientific lab in the United States, established in 1901. There are two chapters, one in Boulder and one in Maryland. So I'm from Maryland. And this Atom GPT is the part of a project called Jarvis, which is available at jarvis.nist.gov. So let's talk about what's inverse material design first. So as a material scientist, we know it's processing, structure, property, performance, relationship. Now you can take the other way. That's inverse material design. So instead of going from structure to property, we are trying to go from property to structure. And when I say property, it might mean different things. It might mean scalar properties like band gap, elastic constant, absorption strength, whatever. Spectra, such as X-ray diffraction, neutron diffraction, or images, such as microscopy images. Now we want to go back from these properties to structure, which is the idea of inverse material design. Now the concept is not new. It was proposed way ago by Alex Zunger and a group of workers. You can see this really nice paper called Inverse Design in Search of Materials with Target Functionalities. All right, so now, although this idea of inverse material design sounds pretty fancy, there are several challenges. Number one, there are methods out there, but they're very limited to the complexity they can handle. For example, cluster expansion or genetic algorithm, Monte Carlo, and so on. Also, we need well-curated data sets and very well-defined benchmarking platform to guide this inverse design processes. So these two are extremely important. Now, because to my knowledge, at least, there are no unified model for inverse material design. The only probably resource we have is AI models. Now, when I talk about AI model, it can be different types of model, fingerprint-based model like linear regression or so on, or GNN or GPT model. So which one should I use? And recently in 2023, we used the diffusion and GNN-based model to design inverse design superconductors. It was published in, let me see if this one works. Maybe not. Anyways. Yeah, so we use this inverse design approach for superconductors in 2023, and Atom GPT was published just a few months ago. So maybe that's why you're not familiar with it, but I think you'll be quite impressed by this. All right, so I talked about it, databases. So we need good database, diverse and well-calibrated database, which is one of them is provided by the Jarvis, which is available at jarvis.nist.gov. If you go to the website, there are certain databases, web apps, tools, tutorials, outreach events, more than 50 resources out there. Initially, it was funded from Materials Genome Initiative, and now it's being funded from the US CHIPS Act. And the idea is to combine density functional theory, force field machine learning, and several benchmarking tools to guide or design new materials. Now, so some success story. So starting in 2017, we have about 50 articles published from this, about 3,000 citations. We are very proud. We have about 150,000 users worldwide. Probably there's no country in the world which is not using Jarvis. It has about 80,000 materials and millions of properties calculated. Most of our data is on a fixed share, so we just hit 1 million download on fixed share, and our code is also 1 million download as well. So recently, NIST used US CHIPS Act, which is the biggest investment by US government, bigger than Manhattan Project. There's a component for strategic plan, and in the strategic plan, Jarvis was highlighted as making the computational standards. We are very proud about that. So that was Jarvis database. Now we need to learn about the benchmarking. Now, every year, I feel like there are multiple benchmarking platforms, but what we want to distinguish from is reproducible benchmarking. Just because you read a benchmarking paper does not mean it's reproducible. I would like to bring your attention to this paper on Nature called 1,500 Scientists Lift the Lid on Reproducibility. So in this paper, there was a survey conducted by several scientists in different fields. How much percentage of papers are reproducible? Any guess from the audience? How much percentage of papers are reproducible? 12%. Close enough. So in this paper, they show that only 0.5% in certain field to 30% papers are reproducible. More than 70% papers are non-reproducible. Of course, it depends on the domain of the knowledge. This is a great, big challenge that we need to focus as a community. So reproducibility, benchmarking, and not just AI/ML, although this is a hot topic, AI/ML. There are other things like electronic structure benchmarking, force field quantum computation experiments. There are currently over 300 benchmarks in Jarvis leaderboard. And it's very flexible to add new benchmarks and add new contributions. Now, when I talk about benchmark, there are two main components to it. First called benchmarks and second called contributions. A benchmark is a reference point which must have a peer-reviewed DOI article with this. This is a minimum criteria to call that a benchmark. Now, for electronic structure calculations like DFT or tight binding, it's experimental data we compare to. For artificial intelligence, the test data. For force field, it's electronic structure. For quantum computation, it's analytical result. And for experiments, other experimental results. So this paper on Jarvis leaderboard was just published this year, and almost all the national labs kind of participated here in this work, and several universities. And it's a very flexible framework to contribute to. So we talked about first database, we talked about benchmarking platform. Now let's talk about what kind of AI model to use. So first we'll talk about the graph numerical model. So atomic structure models can be represented by many of you have heard today in the talk as atomic structure. So for example, in this cute picture here, you can see the blue and the red balls or spheres. You can see this silicon and oxygen. One way to distinguish them is using atomic number, boiling point, and so on. That's called node features. Now we want to distinguish between edges or bonds. So you can, again, different materials will have different number of bonds. So what you want to do is kind of take all these bonds and do some sort of radial basis expansion or something like this to kind of have a homogeneous representation. Now this is fine until 2017. These people were using GNN and so on. When we started working on this, they missed a very crucial information, bond angles. So then a line graph was proposed from our group. And the idea was, if this is a node and these are the edges, you can compare a new graph where the edges are the nodes and the edge pair are the new edges. So in that way, you can capture angles. And if you take a line graph, you can get dihedral angle and so on. So a very flexible framework. So it was published in 2021. It's a very highly cited papers right now. And you can see this work was used for several projects, such as property prediction. We were also one of the first unified force field graph unit of force field developers, especially for solid state materials, and based on Jarvis DFT data for designing superconductors, carbon capture materials, phonon density of states, electron density of states, and so on. It's available on US NIST websites aligned. So one of the applications which is relevant for this work is, this is a preprint we just put on our CAM archive. It's called Examining Generalizability of AI Models for Catalysis. Now, in catalysis, I feel like there are three types of models for machine learning: problem-specific, domain-specific, and unified models. So a problem-specific model, for example, TINNET model we heard in the beginning of the talk, there's a special like nitrogen adsorption to certain catalysts we want to study. So that's problem-specific. It's not super expensive. It's cheap to train. There are domain-specific models like Open Catalyst Project, for example, and this can be very expensive. Now, there are unified models which are trained on bulk data with no catalyst, no surface, no defects, probably just bulk data. And that can still be generalizable enough for a large task, including catalysis. So that's three types of model. Now, how do you benchmark this? So there are several databases out there. So in this paper, at least, what we did is this TINNET, AGR, TINNET is from Virginia Tech dataset, AGRA from the somewhere in Canada. And we took these two data sets for nitrogen, oxygen, hydroxyl group, and several other functionalities. And then we use a train test split for a particular model, but we also extended, what if the model was trained on nitrogen? How did it predict on oxygen? Okay, so it's very different kind of idea. So we saw that even though the model, especially for nitrogen, it was still quite generalizable for oxygen, hydrogen, which is very interesting. So this was fine. The fun part was the OCP-based model, which was trained on the OCP, I think, 500,000 data set. It was also generalizable for all these catalysts. And most importantly, very recently, with all these unified force field models, we compared Align, MatGL, ChargeNet, MACE. So we found the best model for this benchmark was ChargeNet, and followed by AlignFF. And so we took this AlignFF models and we made an app called Jarvis Catalysis, available at Jarvis or NIST.gov. That's J-Catalysis, where you can put the substrate and substrate plus the adsorbate atom. It will calculate the energy of these two and calculate the adsorbate energy, and from there calculate the adsorption strength. So that was GNN models. You can also use this for making inverse design. So this was the idea. You can take the graph network, and from the hidden feature, you can predict like lattice constant, elemental type, and coordinates, and you can denoise it to kind of predict new structures. So this was a model called CDVAE, and we used this to generate new superconductors, which is available in Journal of Physical Chemistry later article last year. That is fine, but although this method is really amazing, this model is really amazing, and one of the most promising model, it is very slow and very hard to train, I feel like. So this is where GPT and Atom GPT comes into play. Now, at this point, we have heard about Chat GPT, But if you look for the ChatGPT models and ask a prompt like, here is the prompt, give me superconducting transistor temperature, it might not work very well. Also, the models are proprietary and it changes every time. There is no guarantee it will be reproducible. This is a problem as a scientific community. So to solve these problems, we propose Atom GPT, which is can leverage the material science domain knowledge, and it's an open access model. It can be used for both forward material design and inverse material design. For example, you can give a prompt. This is for a case of superconductors, but it can be catalyst or anything. So like magnesium boride is a hexagonal material. This is the bond length. Predict me this transition temperature. Or you can give an inverse prompt where here is a description of a superconductor material. This is my formula. This is a TC I want. Generate me the crystal structure in a text format, and this will generate the text format. This was published, as I said, this year, and I won't have time to go details of this, but this is based on the transformer architecture. This is the highest, I think, one of the highest cited article in computer science literature. And most of these models are available on Hugging Face. There are many, many models in Hugging Face. The one we are using is called Mistral, AI 7 billion models. And instead of using the entire model, we use something called PEF, or parameter efficient fine tuning, where you kind of don't touch many of these parameters and just fine tune certain level. And also you use mixed precision models. So instead of using 16-bit or B float 16, you use 8-bit or 4-bit, or even nowadays they are 1.1-bit model. So yeah, that's how we try to kind of leverage this, how to tune this model. And my fine-tuned model on TC superconductivity is also available in Hugging Face, and several hundred times downloaded already, so you can check it out. So again, I won't have time for details of this, but I want to point out very important automatic mixed precision is very important. And another very important topic is rotary projection embedding. Now, if you take a look at a dictionary, do you know how many words are there in a dictionary? Any guess? There are about 200,000 words, suppose. So you don't want to, if you will take all these 200 words and give it 1, 2, 3, and all these numbers, and call this, and you say a sentence, I am a man, or something like this, you can give this tokens and then establish the relationship between them using something like a transformer model. Now, you can do this in a linear way, but there also sometimes there's a relation which is kind of related to each other. That's why this row former model or rotary position embedding model was extremely useful for this kind of task, and which was used in this work. So in our model, and not just talk, not just papers, you can actually try this model right now, today, on your phone. You don't even need to download anything. So you can try to train a forward model on your phone on this one, and the inverse model, and interact with Hugging Face model. So feel free to check it out. And we compared with these models with other existing models like CGCNN, Align, and Atom GPT was kind of pretty good, especially for electronic properties for these models, and also not for forward models. So for inverse model, it was pretty accurate enough, more than 3-4 times than something like CDVAE. As I said, it's very important to have a benchmarking platform. Most of this data is available on Jarvis Leaderboard and AtomGen. And if you have a new models in this task, you can also upload there and see, kind of calibrate this. So in this process, we actually computationally discovered new superconductor called NB2B, and we actually validated it using Macmillan-Allen formulation that it was actually superconductor. Now that is fine for scalar properties. Now we want to go beyond this, and we want to have a vector properties or spectra properties. So this is I actually learned X-ray diffraction last year. So I measured magnesium boride and lanthanum boride X-ray diffraction peak. Then you have to do something like background subtraction. Now you can take this as a string, tokenize it, put to the transformer model, and train it to generate crystal structure. So you'll say, this is the element guess I have, this is the spectra I have, can you generate me a full atomic structure? And this model is working beautifully. And NIST has asked me to, before I publish, I patent this. So it's under patent progress right now. And not just X-ray diffraction, we are having model for Raman spectra, NMR spectra, and so on. So this will be coming on soon. So with this, I highlighted to you NIST Jarvis database. I encourage you to check it out. It's a huge resource for many databases, tool, machine learning. Jarvis Catalysis apps, especially probably relevant for this community. These are kind of benchmarking and also tools to do catalysis. Jarvis Leaderboard benchmarking platform, Atom GPT. We also have upcoming events called Artificial Intelligence for Material Science every July, and QMS, Quantum Matters for Material Science, every January. We really are serious about reproducibility. We are going to have a hackathon called Reproducibility Hackathon, or RepRo Hack. Also, if you are you are looking for a postdoc and you have US citizenship, feel free to reach out to work with me. We have a deadline in February 1 and August. And there are some contact information. This is a website. You can follow me on Twitter, LinkedIn. I also have a YouTube channel where I make videos about these things. So feel free to subscribe and like my channel. And this is my email. Thank you.
Questions or comments? Anybody else?
Well, with the generative work, we've recently been kind of characterizing the previous way we did things where we would screen millions of candidates and then filter for a small number of good things versus try to generate the good things more directly. But one thing we haven't had a good handle on is like the data requirements. The generative thing does that fast, but it still has a data requirement. Is it similar in your experience on both of these sides? Like, do you still need millions of things to train the distribution you're generating from? And if so, is it actually like a better approach than simply having done that?
Good question. So I would like to give an example that the superconductor work is trained on only 1,000 data, and it was still able to generate good atomic structures. So it does not require huge millions or whatever data points.
Are those 1,000 already the things you're generating though?
No.
Like how?
What is it? What do you mean? Like, suppose I have a lot of magnesium boride superconductor and so on, and now I said I want to have a material on magnesium boron nitride. It will generate the crystal structure of magnesium boron nitride.
Yeah, but if you generate things that are far from the distribution you trained it on, how is it any good?
How is it? And so you have to always validate with DFT. So that's why we do validate it. And most of the case, superconductor transistor temper is very computationally expensive. So whatever we tested for more than, I think, 30% cases, it was actually superconductor. So it's not 100% or something, but having something like this is still promising. And of course, with more data, I feel like there's more opportunities.
Okay. There are no more questions for you. Thank you. We're taking Montoya from the research industry.
Oh,
All right. Can I ask a question actually real quick, which is
Social science and
yeah,
climate.
sure.